You've got some kind of object that you're pushing down on at an angle theta. It says that the angle is theta is with respect to this horizontal ground over here. Now, what forces are acting on this mass right here? Well, if I were to track this force, the F push, I still have my weight, which I'm going to call W. That's equal to mg. And I've got the ground pushing it against the box or the object, and that's called the normal force. Now, this Fp over here, it's at an angle, it's a vector, we should break it up into its components. That's kind of the thing that you always do. So we're going to make a Fpx and an Fpy. And that's pretty straightforward to do. Let's see, if this is theta, this is also theta, Fpx is equal to Fp cosine theta, and Fpy is equal to Fp sine theta. Now, what happens is, see this normal force, it kind of balances out all of the normal force is the ground pushing on the object. Now, if the object is not accelerating, which in this case, it's not accelerating in the vertical direction, in the y direction. It's not going up, it's not going down. If anything, it's going to slide across the ground like this, but it's not going to break the ground and fall down. And for some reason, the normal force isn't going to be bigger than these two forces over here, causing it to like fly up in the air. I mean, wouldn't that be crazy? You're leaning on a desk and all of a sudden the desk starts flying in the air. That doesn't make any sense. So the acceleration that this object will undergo in the vertical direction will be zero. What's going to happen is this normal force, this up-pushing force, will have to balance out not only the weight, but also the vertical component of the force that you're pushing on it with. So if I were to add all the forces in the y direction and make that equal to mass times acceleration in the y direction, the acceleration in the y direction here is going to be zero, right? Because we said that it's not falling into the ground or rising up into the air. Your normal, or so if I were to account for all of the forces that I see acting on this box that is in the vertical direction, I see the Fpy, that guy right there, but he's negative because he's pushing down. I see the normal force, that's positive, pushing up, and I see the negative weight is equal to zero. So if I wanted to solve for the normal force that I would get, I would end up getting n equals Fpy plus W, and I can replace Fpy with what it is, so normal force is equal to Fp sine theta plus W. Now, I think that the next part is, why don't we do a few more things that we should talk about this thing, with this problem a little bit more. If I were to do some of the forces in the x direction, equal to mass times acceleration in the x direction, the only force that I see acting on this box that's going in the horizontal direction is this guy right here. I guess the first question I should ask myself is this acceleration zero? And the answer is no, it's not zero, because it could be accelerating in the x direction. So I'm going to leave that here. I'm not going to just cross it out like I did here, make it zero. I'm going to leave that there. And then the second question I ask is, well, what forces do I see acting in the x direction? I only see this one. So Fp cosine theta equals max. And you want to solve for what the acceleration is, maybe, and your acceleration is equal to Fp cosine theta over m. Which, if you check the units of force is in newtons. Newtons is also known as a kilogram meters per second squared. The units of cosine theta is nothing. The units of mass is kilograms. So you end up with meters per second squared, which is good because that's your acceleration that you want. Some things that I want to kind of analyze about this with you is this. What if theta equals, let's say, 90 degrees? If theta equals 90 degrees, the cosine of 90, if you plug that into your calculator, make sure your calculator is in degrees, the cosine of 90 is actually 0. So your acceleration in the x direction is going to be Fp times 0 divided by m. Well, that's going to be 0. Your acceleration is going to be 0, which kind of makes perfect sense to me because it tells me that if theta were 90 degrees, I would be pushing my force with an angle of 90 degrees. I would be pushing this thing straight down. What is its acceleration? Well, its acceleration would be 0. It would not be moving in the horizontal direction. I mean, you think about it. If there's a crate and you stand right on top of that crate, then that thing's not going to move to the right or left. Also, if theta is 90 degrees, then my normal force is going to equal to, well, the sine of 90 degrees is equal to 1. So my normal force is going to be equal to Fp times 1 plus W. Well, that makes sense to me as well, because if I'm talking about theta being 90 degrees, I'm pushing straight down on this thing, and the normal force has to counteract both the weight of my object plus the amount of force that I push down on it. All of that force. If I push 90 pounds down, then it's going to have to balance 90 pounds in addition to whatever the weight of that object is. And then you can kind of think to yourself, okay, well, what if theta equals 0 degrees? Then my normal force is equal to, by the way, the sine of 0 is 0, so my normal force is just equal to the weight. But that makes perfect sense too, because if I'm pushing this thing purely in the horizontal direction, then the normal force that it's pushing up is only going to equal to the weight pushing down, because there's no vertical component to that force push that I have. I think that the question is, as I increase the angle, what happens to my to the normal force? Well, as you increase the angle between 0 degrees all the way up to 90 degrees, it goes from W to Fp W, or to Fp plus W. So it's going to go from W to something bigger. Basically what's going to happen is your normal force is going to have to get bigger and bigger and bigger to counterbalance the bigger and bigger vertical components of your force push in the first place. Did I explain that to you well enough? Did that make sense?